Today, we're diving into a hidden science, an invisible force that literally powers everything around us, from the coffee you drink in the morning to the fuel that gets you to work. We're going to break down how we separate the world, molecule by molecule.
So, here's our game plan. We're going to start with the unseen movement of molecules all around us, and then look at the rules that tell them where to go. After that, we'll see how we use heat to separate things, talk about why the real world is messier than the textbook, and finish up by exploring the incredible toolkit engineers use for distillation. Okay, let's kick things off with something you've experienced a million times, but maybe never really thought about what's happening on a microscopic level.
I mean, it really does feel like a little bit of magic, right? You crack open a fresh can of coffee and suddenly that amazing smell is everywhere. Well, that everyday magic, it's all thanks to a fundamental concept in chemical engineering.
It's called mass transfer. And really, the idea is incredibly simple. Molecules just don't like being crammed together. They have this natural urge to spread out, to move from a place where there's a whole bunch of them to a place where there are fewer.
And the engine that drives this whole thing is a process called diffusion. You could just picture it. All those individual molecules are constantly jiggling, bouncing, and moving around randomly. And it's that constant chaotic motion that causes them to spread out and fill whatever space they're in.
Now, here's the thing. Not all diffusion is created equal. You've got two main flavors. First, there's molecular diffusion. Think of a drop of food coloring slowly, almost beautifully, spreading out in a glass of still water. That's slow. Then you have convective diffusion. That's when you take a spoon and stir that water. The bulk movement of the fluid mixes everything up almost instantly. It's fast and it's powerful.
Okay, so we've got the basic idea that molecules like to spread out. But how do we go from a general idea to a precise mathematical rule that lets us predict and control this invisible movement? Well, to do that, engineers needed a way to measure it. And that's where a concept called molar flux comes in. Honestly, the best way to think about it is like a traffic report for molecules. It tells you exactly how many are crossing a certain line over a certain amount of time. It's basically the speed of diffusion.
And here's the really cool part. That speed isn't just random. It's predictable, thanks to a wonderfully simple rule called Fick's law. All it really says is that the bigger the difference in concentration, the steeper the molecular hill, the faster the molecules are going to rush downhill to even things out.
And, there's this one little detail in the math that I just find so elegant. It's this tiny negative sign in the equation. And all that little sign does is tell us something we already intuitively know. The flow is always downhill, always from a crowded place to an empty one. Simple but profound.
All right, we have the fundamental rules of how molecules move. So let's zoom out now and see how we harness those rules to perform one of the most critical industrial processes in the entire world, distillation.
So, what is distillation? At its heart, it's just a really clever trick using mass transfer. It all comes down to a simple fact. Different liquids boil at different temperatures. So you take a mixture, you heat it up, and the liquid with the lower boiling point turns into a vapor first. You just capture that vapor, cool it down, and boom, you have a pure substance. The whole entire process relies on understanding the relationship between a liquid and the vapor it produces. We can actually map that relationship on a chart called a vapor-liquid equilibrium curve, or a VLE curve. You can think of it as a cheat sheet for distillation. It tells us exactly what the vapor is going to look like at any given temperature.
Now, in a perfect world, in what we call an ideal mixture where all the different molecules get along perfectly, we can predict this behavior with amazing accuracy using a rule called Raoult's law. This is the best-case textbook scenario for any separation.
But, as you've probably figured out, the real world is almost never that simple, or that perfect. Sometimes, mixtures just refuse to play by the rules.
And that leads us to these really fascinating but very tricky mixtures called azeotropes. See, at one specific concentration, they form this stubborn blend where the vapor that boils off has the exact same mix of molecules as the liquid it left behind. That makes them impossible to separate with simple distillation. It's like they're locked together.
And you can actually see these weird behaviors. Some mixtures are more eager to turn into a vapor than Raoult's law says they should be. We call that a positive deviation. Others are less eager, creating a lower pressure. That's a negative deviation. But either way, they can create that one sticky point, that azeotrope, where the whole separation process just grinds to a halt.
Okay, so if we have these simple mixtures, but also these incredibly difficult ones, how in the world do engineers actually get anything done? Well, it turns out they've built up a pretty impressive toolkit over the years.
And here it is. It's a whole range of different distillation methods. It's kind of like a mechanic's workshop. You wouldn't use the same wrench for every single bolt, right? Same idea here. There's a specialized tool for every job, from the most basic separations to incredibly complex techniques designed specifically to break apart those stubborn azeotropes.
But the undisputed champion, the industrial workhorse that processes millions of barrels of crude oil every single day, turning it into gasoline, jet fuel, and all the building blocks for our modern world, that is fractional distillation. It is, no joke, a cornerstone of our civilization.
All of this work happens inside these gigantic structures called distillation columns. And a great way to picture them is as a whole series of many distillations stacked one on top of the other. As the hot vapor rises up the column, it cools, condenses, and reboils again and again, getting purer and purer with every single step. And inside these columns, you have these trays. They are the absolute heart of the whole operation. This is where the magic happens. They create a massive amount of surface area, forcing the rising hot vapor to mix with the cooler falling liquid. This is what allows that crucial mass transfer to happen over and over again.
So what's the result of all this invisible science? Thousands, literally thousands of products we use every day without a second thought. The clean water we drink, the fuel we use, even the spirits in a good cocktail, and the plastics that make our phones, none of it would be possible without mastering this unseen force.
And that really just leaves us with one final thought. We've managed to build so much of our world simply by figuring out the rules of how molecules move. It just makes you wonder, what's next? What other invisible forces are out there just waiting for us to figure them out?